Hello everyone, welcome to the presentation of our work titled as Stochastic Binary Network for Universal Domain Adaptation. Unsupervised domain adaptation deals with the problem of knowledge transfer from labeled source domain to an unlabeled target domain under domain shift. In this work, we focus on more practical problem of universal domain adaptation, which consists of additional problem of label shift between source and target domain. Hence, source and target domain consists of some private classes. In universal domain adaptation, our goal is to learn a classifier which can classify target samples to either one of the known classes or to a separate unknown class. Now we will discuss what are the major challenges in universal domain adaptation and our proposed solutions to tackle them. First major and widely ignored challenge is overfitting from source domain, in which lack of supervision from target samples causes detection criterion to be overfitted from source samples. We tackle this problem from newer perspective by using stochastic binary network, where we treats classifier weight as a random variable rather than a point weight vector, and then used Gaussian distribution to model this. Now, we can draw samples from this distribution to obtain various distinct yet plausible classifiers, without causing substantial increase in model size or training time. Second challenge is private class detection and common class alignment. It occurs due to the presence of both private and common classes in universal domain adaptation. To tackle this challenge, we propose a novel confidence score estimation technique to find the confidence scores for source and target samples using consistency between the outputs of sampled stochastic binary networks. These scores enable common class alignment during adversarial learning by giving higher weights to the samples belonging to the shared classes across domains. Finally, the third challenge is fragmented feature distributions of the target domain. To tackle this challenge, we incorporate deep discriminative clustering in our framework to formulate a loss function. This enforces the structural regularization and enables learning of compact clusters in the target domain. Given figure represents our entire framework. Our framework consists of four main components. First is hard negative classifier sampling and entropy minimization. Second is confidence score estimation technique. Third is weighted adversarial learning, and finally consistency regularization. Initially, data is passed through feature extractor. Now these extracted features are passed through our first component, that is hard negative classifier sampling and entropy minimization. Let's first understand what is hard negative classifier sampling. Our stochastic binary network consists of CS binary classifiers, one for each source domain class. In this, each binary classifier outputs a two-dimensional vector denoting the probability of a sample being an outlier and inlier respectively. For each source sample, the class corresponding to the given label is considered positive, and all other classes are considered negative. Now, we can train binary classifier corresponding to the positive class to predict input as inlier. But, now a question arises of how to train classifiers belonging to negative classes? One simplest approach is to train all classifiers of negative classes to predict input as an outlier. But this approach is both time and compute intensive. Hence, we used hard negative classifier sampling in our framework. In HNCS, for each sample, only two classifiers belonging to the positive and the nearest negative class will be trained. Finally, our one versus all loss can be written as follows. Through first part of this loss, we are making our stochastic binary network to predict input as an inlier for positive class. And with the help of second part of this loss, we are making our stochastic binary network to predict input as an outlier for hard negative class. Now, let's understand entropy minimization. For the target samples, we use open set entropy minimization. In this, we compute the entropy of all the binary classifiers of our stochastic binary network, and take the average and then train the model to minimize this. Hence, our entropy minimization loss can be written as follows. This loss helps us in achieving low density separation, while keeping unknown as unknown. This unique capability of keeping unknown as unknown is achieved by using binary classifier because it incorporates concept of unknown. Now, let's understand second component of our framework, which is our novel proposed confidence score estimation technique. It consists of four main steps. First step is to sample M stochastic binary networks from Gaussian distribution. Second step is to pass features of source and target data through each stochastic binary network to generate M independent CS times two-dimensional outputs. Third step is to perform average operation to generate final output for a given sample. Finally, confidence score will be calculated by taking maximum inlier probability of the final output. Now, the samples exhibiting larger scores will most likely belong to the common classes, because the likelihood that all networks will commit the same mistake of considering the sample as inlier with high probability is very minimal. Now, let's understand third component of our framework, which is weighted adversarial learning. Adversarial learning is a powerful technique for reducing feature discrepancy and discovering invariant representations in domain adaptation. But, due to the label shift, incorporating adversarial learning directly into our framework would result in significant negative transfer. To rectify this, we introduce adversarial learning weighted by confidence scores for common class alignment. And it can be written as follows. It contains a feature extractor F and an adversarial domain discriminator D, where D aims to differentiate the source domain from the target domain, while the F tries to learn the domain invariant representations to fool the D. Finally, the last component of our framework is consistency regularization via deep discriminative clustering. Consistency regularization is the powerful solution for learning compact representations in semi-supervised learning. And fixmatch is one of the representative of it. Fixmatch promotes compact clusters by using the confident predictions of weakly augmented unlabeled data as the pseudo-labels for strongly augmented unlabeled data predictions, and it can be written as follows. Fixmatch loss suffers from two major problems. First problem is that confident predictions are calculated using the output of only one classifier, leading to suboptimal performance. And second problem is simply using hard labels will not enhance cluster size balance, which is crucial due to the absence of prior information about the target distribution. Hence we use deep discriminative clustering. Now, advantage of this is that it introduces auxiliary distribution that is soft label by considering overall feature structure in the target domain. Let PT denotes the collective predicted probability outputs for target data. Then the auxiliary distribution QT for the same can be calculated as follows. Kindly refer to our main paper for more details. Finally, an improved form of fixmatch loss by using generated auxiliary distribution as soft labels for predictions of strongly augmented target data can be written as follows. In the given loss, CI represents confidence scores for the given target sample, which are robust because they are based on consistency of M-sampled stochastic binary networks. Now, by combining all these four components, we obtained our novel framework, titled a Stochastic Binary Network for Universal Domain Adaptation. Now in this slide, we will discuss our results. Our method consistently outperforms other baselines across all three datasets in the open set domain adaptation setting. Similarly, our method also achieves new state-of-the-art across all three datasets in the most challenging universal domain adaptation setting. Especially, on the large-scale visual domain adaptation dataset where our method gives 8.5% improvement in H-score. This table shows the significance of stochastic classifiers where a drop of 2% in overall H-score is observed on replacing stochastic classifiers with conventional classifiers. Notably, this decline remains consistent across all adaptation scenarios and becomes more pronounced in complex adaptation settings like A2W and D2A. This figure examines the behavior of our framework on varying number of target private classes. Remarkably, our framework consistently outperforms other baselines under the different values of target private classes. Of particular note, only a smaller drop of 1.4% in H-score is observed on varying value from 5 to 50, which underscores the robustness of our method on varying degrees of openness. These are some of the references. Please refer to our paper for more details, and thank you.